All right, let's just jump straight into it. Welcome to The Explainer. Today, we are tackling one of the most notoriously tricky areas of the entire Cambridge mathematics syllabus. Seriously, whether you're sitting for the 0580, the 0606 additional maths, 4024, 4037, or even the 4040, there is a very specific type of question that consistently trips up even the absolute best, most prepared students. And yes, I'm talking about permutations and combinations. Now, I want you to picture a real Cambridge past paper question right in front of you. It's one of those massive word problems. And usually we see two types of students tackle it. Let's call them Alex and Sam. Alex is our overloader. Alex reads the question, immediately starts panicking, and tries to manually list out every single mathematical possibility by hand. There's no analysis happening, just pure, exhausting brute force. Alex is writing down combination after combination until time simply runs out. Then we have Sam. Sam rushes. Sam is racing against the clock, sees a bunch of numbers in the text, blindly guesses a formula, and completely misses the specific command word requirements in the question. Sam ends up with an answer that makes absolutely zero logical sense. If you were the examiner looking at their papers, you'd just be piling up the red pen marks on both of them. But that's not going to be you. Our goal today is to completely transform those red marks into green check marks. We are going to build a mental toolkit, a mathematics success blueprint that turns these complex, intimidating puzzles into incredibly simple, solvable steps. We're going to learn exactly how to read the examiner's warning signs and avoid those common pitfalls that completely sink grades. So, let's get into it.
I really want to anchor our explainer today with this absolutely brilliant quote, "It always seems impossible until it is done," by Nelson Mandela. Think about that feeling when you flip open your exam booklet. You're stressed, the clock is ticking, and you see this massive paragraph asking you to arrange, say, 15 different objects with bizarre, highly specific conditions. Your brain's first reaction, sheer panic, right? It feels literally impossible. And hey, advanced discrete math can absolutely feel overwhelming. It's designed to test your limits. But, and this brilliantly illustrates our core philosophy today, it only feels impossible until you actually possess the right analytical tools. Once you understand the underlying machinery of how these specific problems are built, you'll realize they aren't impossible at all. They're actually just simple locks, and you're just waiting to use the right key.
Speaking of locks, let's actually look at a very practical example straight from our source material to show you what I mean. Imagine a standard combination lock, like the one you might use at the gym, with 4 numbers. For each of the 4 individual slots, you have exactly 6 choices, the digits 1 through 6. Now, if you're stuck in the mindset of our student Alex, you might think, well, I don't know the code, I'll just guess them all systematically. Let's actually do the math on that strategy. You have 6 choices for the very first number, then you have 6 choices for the second, 6 for the third, and 6 for the fourth. That is 6 times 6 times 6 times 6. That calculates out to 1,296 possible combinations. Now think about this. Even if it takes you just 10 seconds to test each combination, systematically working your way through all 1,296 possibilities is going to take you over 3.5 hours to crack. Obviously, in a high-stakes exam setting, you do not have 3.5 hours to brute force a single solution. You need a streamlined, foolproof strategy to cut through the noise.
And that brings us to the game plan. We are going to build your mathematical mastery in 3 distinct levels today: factorials, permutations, and combinations. But we aren't just going to look at the formulas. We're going to apply an analytical framework to completely decode the exam command words. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's get into the mechanics of how top-tier students actually structure their discrete math answers to guarantee those top marks. We're starting at level 1, factorials. Think of these as your foundational building blocks.
Let's introduce this foundational concept using a highly relatable everyday example. We have a student named Winnie, and she's just tidying up her bookshelf. She has exactly 5 math books, and she wants to place them all together in a row. The typical Cambridge exam question would simply ask, in how many different ways can she arrange them? Our rushing student, Sam, might just write down the number 5 and sprint to the next question. 0 marks. We need to analyze this situation methodically. Let's walk through the actual logic step by step. Imagine the completely empty shelf. For the very first space on the left side of that shelf, Winnie is holding 5 possible books. She can choose any of them, so she has 5 choices. Step 1 is done. Now she moves to the second space. She's already placed 1 book down, right? So she only has 4 choices left in her hands. For the third space on the shelf, she has 3 choices. For the fourth space, 2 choices. And for that final, 5th space, there's literally only 1 book remaining. Because we are making these choices one after the exact other, in sequence, we multiply them all together. 5 times 4 times 3 times 2 times 1. That equals 120 total unique arrangements. This decreasing multiplication sequence is literally the heartbeat of discrete math.
And that brings us to our formal definition. That exact calculation we just did, 5 times 4 times 3 times 2 times 1, is called 5 factorial. Mathematically, it's written as a 5 followed by an exclamation mark, so 5 factorial. Generally speaking, the factorial of any number, let's call it n, represents the absolute total number of ways of placing n different objects in a line. You calculate it by taking your number and multiplying it by every single positive integer less than it, all the way down to 1. Oh, and listen closely, because here is a massive trap that Cambridge examiners absolutely love to set for you. What happens if you have 0 items? By a very special mathematical convention, 0 factorial is always taken to be exactly 1. Do not put 0. Remember that rule because it will literally save your grade when they try to trick you.
Now, what's genuinely wild about this concept is the sheer scale of factorial growth. I want you to really think about this number, 3,628,800. What exactly is this? This is just 10 factorial. If you have just 10 different items, let's say it's just 10 students standing in a lunch line, there are over 3.6 million different ways to arrange them. Factorials escalate incredibly quickly. This is exactly why our student Alex fails every single time he tries to manually list outcomes in the exam hall. You simply cannot rely on counting these things in your head or jotting them in the margins. You must trust the mathematical formula. By confidently writing down 10, instead of trying to map it out, you instantly convert a potential red pen mark into a beautiful green check mark from the examiner.
All right, moving up to level 2, permutations. And the critical phrase to burn into your memory here is order matters. So we've mastered the basic building blocks, but this is exactly where the exam questions start to get a bit spicy. We are no longer just arranging all the books on a single shelf. We are now upgrading our toolkit to focus on scenarios with strict hierarchies. These are situations where we are only selecting a very specific portion of a much larger group. And like I said, the golden rule for permutations is order matters. Let's illustrate this with an example straight from the syllabus. We have a school cookery competition with 10 total contestants. Our friend Joita claims she correctly predicted the exact top 3 contestants, specifically who got first place, who got second place, and who got third place, before the results were even announced. The exam question is, how many different ways could the top 3 have been chosen from the entire pool of 10? Here, we absolutely must apply our analytical framework. Let's treat it like a structured argument. We identify the scenario, extract our numbers, and then we ask, does order matter? Yes, absolutely. Placing first and winning the gold medal is entirely different from placing third and getting the bronze. This strict hierarchy means we are 100% dealing with a permutation.
So let's break this down logically, step by step. We have 3 specific podium spots to fill from a pool of 10 people. For the gold medal, the first place spot, there are 10 possible contestants who could win it. Once that winner is officially crowned, they are off the board. There are now only 9 contestants left who could possibly take that second place silver medal. And finally, for the third place spot, there are exactly 8 contestants remaining. To find the total number of specific arrangements, we just multiply our choices, exactly like we did with factorials. 10 times 9 times 8. That gives us exactly 720 specific ways this top 3 selection could happen. So Joita essentially had a 1 in 720 chance of purely guessing this correct order. She didn't just guess a group, she guessed a perfectly ordered hierarchy.
And we can easily translate this story directly into algebra using the permutation formula. You'll see this denoted as NPR on your scientific calculator. In this formula, N is our total starting pool of objects or people. So in our story are 10 cookery contestants. The R represents the number of available spots we are actually filling. So our 3 podium places. The actual algebra behind the scenes is n factorial divided by n minus r factorial. If you write down 10p3 on your exam paper, the examiner instantly knows you fully understand the command requirement of the question. You've correctly identified that order matters, and you understand you are systematically selecting a ranked subset from a larger group. You've just locked in your method marks. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Welcome to Level 3, Combinations. This is where we learn what to do when order doesn't matter. All right, it's time for an interactive workshop to really cement this. We need to move to this final tool by asking yourselves a critical question. What happens to the math when that strict hierarchy just completely vanishes? What if there is no first, second, or third place, gold, silver, or bronze? To understand this, let's look at a maths teacher's lottery game. The teacher has numbers 1 through 19 in a hat. A student has to select exactly 6 numbers for their ticket. The teacher then uses a random number machine to draw 6 numbers. If your 6 match the teacher's 6, you win a prize. Okay, let's jump into Challenge 1, Data Scan. I'm going to give you a mental 60-second countdown. Look at this scenario and extract the core mathematical trend. What is the absolute fundamental difference between this lottery game and the cookery competition we literally just looked at? Really think about it. Have you got it? The core difference is the draw itself. When the teacher pulls those winning numbers out, it doesn't matter one bit if they pulled a number 15 first or if they pulled a number 15 last. There's no hierarchy. As long as you have the number 15 somewhere on your ticket, it counts.
So let's move to Challenge 2, Find the Flaw. I want you to spot how a lot of students completely mess this up. Our rushing student Sam sees this exam question. Sam sees 19 total numbers and choose 6, and immediately blindly writes down the permutation formula, 19p6. What is the fundamental flaw here? Where is Sam bleeding marks? The flaw is that a permutation strictly, mathematically, assumes that order matters. If Sam uses 19p6, the math is literally treating picking the sequence 1, 3, 15 as a completely different winning ticket than picking 15, 3, 1. But we know from real life that they are exactly the same winning ticket. It's just a group of numbers. By using permutations, Sam has accidentally calculated thousands and thousands of duplicate tickets. Specifically, every single unique set of 6 numbers can be arranged in 6 factorial ways, which, as we know, is 720 ways. To fix Sam's flawed math and get the green checkmark, we must take our permutation, 19p6, and divide it by 6 factorial. This strips out all those useless duplicate arrangements.
And that beautifully and perfectly brings us to the formal definition of a combination. You will see this denoted on your calculator as NCR. A combination is a selection of R objects from N total objects, where the exact order is absolutely 100% not important. Look closely at the formula here. It is the exact same base formula as the permutation, n factorial over n minus r factorial, but with one absolutely crucial addition. We multiply the denominator by r factorial. This extra step mathematically scales down that massive permutation number to properly account for the lack of order, cleanly eliminating all those duplicates we just talked about.
So let's return to our teacher's lottery game and finish the calculation. We have 19 total numbers. We are choosing 6 of them, and we firmly established that order doesn't matter. This is exactly 19c6. If you plug 19c6 into your calculator right now, the answer is exactly 27,132. We'll round it down to 27,000 for simplicity. This reveals that properly applying this combination formula yields approximately 27,000 completely unique sets. This means any given student has roughly a 1 in 27,000 chance of actually winning the teacher's game. This right here is the true power of knowing exactly which formula to deploy and when.
Let's cement the central dichotomy of this entire subject. This is Challenge 3, Speed Writing. Mentally lock this in. This is your ultimate cheat sheet recap graphic right here. Take a mental screenshot of this because this is what gets you the marks. Permutations, finishing order matters. Think of a 60-meter hurdles race. There is a gold, a silver, and a bronze. The specific hierarchy dictates the math. Combinations, order does not matter. Think of choosing a committee. If you are selected for the committee, congratulations, you're on the committee. It doesn't matter at all if your name was called first, second, or fifth. You all have the exact same status. Understanding this specific split is your ultimate key to unlocking top marks on these papers.
Therefore, when you are sitting in that absolutely silent exam hall, sweating a little bit, staring down a complex discrete mathematics puzzle, there is only one anchoring question you must ask yourself. Before you even touch your calculator, before you write down a single number or formula, I want you to ask yourself out loud in your head, does order matter? If the answer is yes because there's a rank or a sequence, you use a permutation. If the answer is no because it's just a general group, you use a combination. It really is that elegantly simple once you consistently apply the strategy.
Okay, let's actually prove that it's this simple. Let's apply our brand new mental toolkit to a real high-stakes past paper question, pulled straight from a November Cambridge paper. Here is the puzzle exactly as it appeared. A school council of 6 people is to be chosen from a total group of 14 people. Specifically, that group is made up of 8 students and 6 teachers. For part 1 of the question, calculate the number of different ways the council can be selected if there are absolutely no restrictions. Look closely at the command phrasing here. We are just choosing a council. The roles are totally unspecified at this stage.
Let's run our structured framework. We need 6 people out of 14 for a general council. Step 1. Identify that these council seats have absolutely no specific ranks. There's no president, no treasurer, no vice president yet. It's just a pool of people. Step 2. Ask our golden question. Does order matter? Because simply being on the council doesn't involve any sort of hierarchy, the answer is a resounding no. Step 3. Because order doesn't matter, we confidently and immediately pivot to our combination tool. We literally just write down 14C6. You plug that into your scientific calculator, and you effortlessly secure full marks for that section. You didn't panic, you didn't overcomplicate it, you just ran the system.
But as you know, Cambridge examiners absolutely love to test if you're actually paying attention to the details. Here comes part 2 of the exam puzzle, and this is where students drop marks. The exam paper now says, after the council is chosen, a chairperson and a secretary have to be selected from the 6 council members. Calculate the number of different ways in which a chairperson and a secretary can be selected. Look at exactly how the exam flips the script on you. They have just seamlessly introduced specific ranked roles. Now, our rushing student Sam is still stuck in combination mode from part 1. Sam skims the text, writes down another C formula, and gets this completely wrong. But not you. You run the framework, you use the system. Step 1, identify that we now have specific ranked roles, a chairperson and a secretary. Step 2, ask the golden question, does order matter? Well, being the chairperson in charge of the whole council is vastly different from being the secretary taking the notes. Yes, order suddenly matters immensely. Step 3, because order matters, we must instantly switch our strategy to our permutation tool. We have a new pool of 6 members, and we are filling exactly 2 specific hierarchical spots. We write down 6P2. Just like that, you've decoded the tricky command words, applied the correct framework, and maxed out your mark potential all the way to 100%. You read the warning signs perfectly.
Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCE and click that bell. Don't let another exam pass you by. So as we wrap up this explainer, I want to leave you with one final provocative thought. When you sit down and face your next impossible-looking exam puzzle, what's the very first question you're going to ask yourself? You now know that mastering this math isn't about memorizing endless lists or guessing formulas. It comes down to confidently applying your 3 core tools: factorials, permutations, and combinations. By simply asking, does order matter, you completely decode the matrix of the test. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.